All right, hello everyone, and welcome to our first video lesson here. Hopefully this goes nice and smoothly. So the very first section that we're going to be looking at today is 9.1, which is net ionic equations and qualitative analysis. So what we're going to do is we're going to break this down into two parts. The first part will be looking at our net ionic equations, and then I'll give you a little bit of break to do some practice questions, and then the second part will be just looking at qualitative analysis, and it should go fairly quickly, and that should take just about the entire class. So I believe right now the camera's working all right. However, sometimes it does fall a little bit behind with the video feed. So if it does stop at any moment, don't worry. It does seem to catch back up to speed after a while. So we'll get started here. So right off the bat, what I want to do is just look at our double displacement reactions that we've already looked at many times before, but this time we're going to look at them a little bit differently. So with our net ionic equations that we're going to be working into, there are two main principles that we're going to look at. One, when our substances are in a solid state, we're going to kind of look at their chemical composition. And then we'll look at what really they're doing once they're in solution or dissolved in water. So with this double displacement reaction here, we're taking silver nitrate and we're reacting it with silver or sodium chromate. And each one of these solutions are going to be aqueous. But before we make each one of these solutions into an aqueous solution by dissolving them into water, they're initially in a solid state. And what happens there is they're actually bonded to each other. So as a solid, right, your AgNO3 is going to be bonded to itself, right? As we know with a lot of our bonding that we've gone over earlier, right? We don't see any charge here. That's because the NO3 is going to have a -1 charge, and the Ag is going to have a +1 charge. So they actually end up canceling each other out, so that there is no charge. And right now, in a solid state, this is very, very stable. Right? So if we put this right next to a solid composition of sodium chromate, we're really not going to see anything happen, because that sodium chromate is also stable. So nothing is really going to happen. And we'll notice this with a lot of our double displacement reactions. Whenever you mix two solids together, you are very rarely going to see a reaction occur, right? Because they are stable when they're bonded to each other. But something unique happens when both of these things are added into water. So in solution, right, we no longer have, let's say right before we put it in, it's AgNO3. Once we put that into the solution, we're going to see that it is going to break up into a variety of Ag+ ions and NO3- ions, right? And when the solution is saturated, there's going to be lots of these things. Right? And they're all kind of floating around independently, right? That is because these charges individually are going to actually start bonding and interacting with the water molecules. As we looked at before when we were discussing our solutions, we need to remember that our water molecules, so our H2Os, are going to be polar in nature. So because our oxygen here is much more electronegative than our hydrogens, it is going to pull the electrons from these bonds up towards itself. And that's going to give it a partially negative charge at this end of the water molecule, and it's going to give it a partially positive charge on the hydrogen side. So this negative charge up here is going to interact with a lot of these Ag+ ions to stabilize them in the solution. And at the same time that that's happening, the opposite side, this positive charge, is going to react with these NO3- ions. And while this is happening, if we make a solution of AgNO3, for the reaction that we're going to discuss in this example with our AgNO3 reacting with our sodium chromate, we're also going to have a solution made up of our sodium chromate. So with these, we do just have to be careful, right? They're not going to fully ionize into Ag, N, and oxygen, all right? With our polyatomic ions, so really anything that you see in your polyatomic ions chart, so with your NO3 here and your CrO4 or your chromate here, right, they do stick together in solution. However, your sodiums are going to be totally by themselves, and your Ags are also going to. So here, we'll see the exact same thing happen. We're going to have a bunch of Na pluses. And then we will have some chromate minuses as well. So you will notice that here I have only included, right, 2 chromates and 4 Na pluses, right? So if you look at the Na pluses, we can see that we're going to have 2 times the amount of Na pluses in our solution than we are going to have our chromate polyatomic ions, right? And this is because in this general compound, right, there are 2 sodiums for every 1 chromate ion. So just keep that in mind, especially when we move on in order to create our net ionic equations. So if we look below, what's actually happening in this reaction is it's not really 2AgNO3 plus Na2CrO4 reacting to produce Ag2CrO4 and it's not really reacting as we see here in order for this to occur, right? Because what we're actually seeing is that on this reactant side, or left-hand side of the equation, these things are all ionized in solution. So that we really don't have a compound of AgNO3 anymore in this solution. Instead, what you're going to see is we are going to have components of Ag plus reacting with components of NO3 minus, reacting with Na plus, and reacting with CrO4 minus. And these multiple things are going to come together in order to make our products of our silver chromate and our sodium nitrate. Right? So it's very interesting that we can start looking at these things as more so of ionic components and less so as their original compounds, because we can see from up here, our original compounds are not actually existent anymore in these solutions. Instead, they're just a bunch of different ions floating around in solution waiting for the opportunity to bond. So what we'll see here is we can see both ionic and net ionic equations. So we're going to introduce both of those here right now. So with our ionic equations, right, we are going to include every single ion. And then once we do that, we can then create our net ionic equation from here. So with an ionic equation for this reaction, I kind of started drawing it on the last page, but it is going to look like 2Ag plus 2NO3 minus 2Na plus CrO4 2 minus, and those are going to react to produce AgCrO4, which is going to be a solid, plus 2Na plus and 2NO3 minuses. All right. Now you will notice I did include one thing in this reaction, our silver chromate. as an entire compound. And the reason for that is that this silver chromate is formed as a precipitate. So it is no longer ionized in the solution. The silver has actually bonded to the chromate ions, forming a solid. Right? So this is why we cannot put these into our ionic form. So looking at this reaction, it's saying that in solution, we have silver ions, we have NO3 minus ions, we have Na plus ions, and we have CrO4 2 minus ions. And when we look at this, we can start to see where we're getting these numbers from. So up here are 2 Ag plus. Well, if we look at this reaction here, we have 2 of our entire AgNO3 there. So this 2 is going to multiply over our Ag and our NO3. So we're going to see that 2 down here with our Ag and with our NO3. Over here, we're going to see that there are 2 NAs. That is because we have 2 Na molecules in here, right? We don't put the 2 as a subscript over here below the Na because once it's ionized, right, those individual sodium ions are going to be on their own. So we're going to say that there are 2 individual Na plus as opposed to an Na2 molecule, because if we wrote an Na2, it would indicate that that Na is bonded to itself. And then finally, we are just going to write a 1 CrO4 2 minus. That's because we have no coefficient up here and we have no external factors on that. And then of course, on the back side of this equation, we have 2 NaNO3s, so we're going to expand that coefficient down so that there are 2 Na pluses and 2 NO3 minuses. And that's essentially how you write an ionic equation. And we'll get lots of practice with this stuff today. So if you're a little bit confused right now, don't worry too much. And then the next thing that we're going to look at is now a net ionic equation. And here it says that we're going to remove spectator ions. So a very important thing to learn is what spectator ions are. So a spectator ion is something that isn't directly involved in the reaction. So if we look here, our overall reaction is really just taking silver and bonding it to chromate ions in order to form silver chromate solid. So if we ever see a precipitate or water being formed, we're going to look at the ions involved that are going to produce our final product, precipitate or water. So in this case, we should look at initially what is going to be involved in order to form this silver chromate. So if we do that, we're going to see that obviously we need silver. Right? So if we go back here, I'm just going to put a little check mark. We're going to need silver. Also, we are going to need chromate. And then we'll notice that what we're left off with is that we have NO3s or nitrates and sodium on both sides of the reaction. And when I see them on both sides, that indicates to me that they're not reacting. They have remained unchanged throughout this entire chemical reaction. So that is what we identify as our spectator ions. If we see something on the left side of the reaction and it remains completely unchanged on the right side of the reaction, we're just going to eliminate those from the equation. So my NO3, I have one here and one over here on the right side of the reaction. So it hasn't changed. It's not involved in the reaction at all. So I'm just going to eliminate that one, and I'm going to eliminate that from our ionic equation. In addition, my Na plus, I am also going to eliminate that because it appears on both sides of the reaction. And with this, I can now look, oh sorry, that's supposed to be an Ag2 CrO4. Right. I can look and I can see, okay, I have Ag reacting with CrO4 2- in order to create Ag2 CrO4. And that is exactly what our net ionic equation is. So I can just write that out at the bottom here, just to simplify everything. So I'm going to have 2 Ag plus reacting with 1 CrO4 2- in order to produce Ag2 CrO4, which is going to be a solid, and both of these are going to be aqueous. Right? And that is your net ionic equation. So what this does is it really simplifies the reaction, and it's really interesting to look at this because it raises a question. Well, does it really matter where things come from? If we have things in solution and we're forming, say, silver chromate, right? It really does not matter where that silver comes from or where our chromate comes from. So let's say in a reaction we're creating still silver chromate. I can get those silver ions and those chromate ions from a variety of different places. It doesn't have to be AgNO3 and our sodium chromate. Instead, let's say I can get it from, let's say, silver acetate. So AgCH3COO. Right? Once in solution, our silver acetate is just going to dissolve into Ag plus ions and CH3COO minus ions. And at the same time, maybe I get my chromate from ammonium chromate, which would be NH4 2CrO4. Right? Again, once these are put into solution, it's just going to make ammonium ions, which are NH4, and it is going to make chromate ions, which are CrO4 2-, and that is going to be plus. So either or here, right? This reaction would still form silver chromate, even if we had different reactants. So our net ionic equation just shows us that we just need to get silver plus ions from somewhere, it doesn't really matter where, and our chromate 2- ions, right? This would be a 2, right? So it doesn't really matter where these things are coming from, as long as we're putting them into solution and we still get a solid precipitate of our silver chromate. So what we're going to look at now is writing our net ionic equations. So there are 3 things in particular that we will see from double displacement reactions resulting from 2 solutions reacting with each other. We're going to focus on 2 of them. So here we have a precipitate which can form, which is going to be a solid, or we can have water that will form, which will be in the form of a liquid. Right? When each of these things form, all right, we will notice that whatever is forming them is going to end up being permanently changed. So as we can see, if there's a reaction and it doesn't form a solid, a liquid, or a gas, then everything is still going to remain in solution, and there's going to be no actual reaction forming. It would all just be spectator ions. So the only time that a reaction will actually form is if we form a solid or a liquid. If nothing forms, there's going to be no reaction forming, because everything, if I just have some greens and some blues, everything in the solution is going to remain ionized by itself. They aren't going to bond to each other. The only time that a reaction is actually going to occur, right, is going to be if some sort of compound, let's say a red and a blue, form and either make a liquid, a solid, or a gas. Right? Because if not, these are all still just spectator ions. Right? There is no reaction occurring whatsoever. So let's look at a sample problem here now. Let's say we have a reaction that forms a precipitate, so we know a reaction has occurred by adding a solution of sodium sulfide to silver nitrate. So sodium sulfide is Na2S and silver nitrate is AgNO3. Right? So first off, just to get started, the very first step that you always want to do is actually write out a balanced chemical equation. With our balanced chemical equation, then we can really easily break things down from there. So we're going to have our Na2S, which is going to be aqueous, added to our AgNO3, which will also be aqueous, and that will react to form NaNO3, so sodium nitrate, and silver to sulfide. Right? Now using this balanced chemical, or this chemical equation, I'm going to quickly balance it here. So on this side I have 2 sodiums, on this side I only have 1, so I'm just going to put a quick 2 in there, right? And then I have 2 NO3s over here, so I'm going to have to put a 2 there, and because I have 2 silvers here and here, right, that is fully balanced. So once I have my fully balanced chemical equation, I can turn it into an ionic equation. So we're going to first start and make an ionic equation. So we're going to identify any of the ions that are going to be produced. But before this, it's very important that we need to identify which one of these, our NaNO3 or our Ag2S, is going to form a solid. Right? We've been told that a precipitate forms, right? So if we consult our solubility tables, we're going to realize that NaNO3 is soluble. But our silver sulfide is not soluble. Right? This is important because we need to include our Ag2S as a solid in our ionic equation. Right? If we don't do that, everything is just going to appear to be spectator ions. So now we can write our ionic equation. So here, let's start off with our very first thing. We have Na2S. So that means that our sodium has 2 sodium, or our Na2S has 2 sodiums. So instead of writing Na2, we're going to write 2 Na+. Right? That is going to be added to an S. Right? If there are 2 positive charges, that means our S, or our sulfur, is going to have a 2- charge. We are going to add that to 2 silver molecules, so 2 Ag+. And because we have a 2 as a coefficient, that's also going to multiply by our nitrates. So it's going to be 2 NO3, 1 minuses. Okay. And that is all going to react to produce 2 sodium molecules, 2 NO3 molecules, and because this is a solid, it is going to stay together. So it's going to make an Ag2S solid, all right, or a precipitate. All right. Now looking at all of these things, right, this is our ionic equation. So in order to make our net ionic equation, what we have to do is cancel out all of our spectator ions. So cancel spectators. So our spectators, again, are the things that are going to remain unchanged from our reactants to our products. So if we look here, I have two Na pluses on the left-hand side of our reaction. I also have two Na pluses on the right side. So those are going to cancel out. They've remained unchanged throughout the reaction. I have an S2 minus, but that remains in our solid precipitate at the end. So I know that that S2 minus is critical for our Ag2S to form. So I'm going to leave that one there. My two Ag pluses are also critical because those are in my solid. However, I have two NO3s on the left-hand side and I have two NO3s on the right-hand side. So those will also cancel. So I'm just going to be left with, I'm just going to write down everything I'm left with, S2 minus plus 2 Ag plus will react to form silver sulfide, which is going to be a solid, this is going to be aqueous, and this is going to be aqueous as well. Okay? And that's how we would form a net ionic equation for a reaction that forms a precipitate. However, this is not the only thing that we can look at. We can also look at a neutralization reaction that forms water. And with this one, we're taking potassium hydroxide and reacting it with hydrogen bromide, right, or hydrobromic acid. And whenever we have an acid and a base reacting together, we know that those two things are going to end up forming water. So again, we're going to start out by just writing out our general balanced equation. So it's going to be HBr, which is going to be aqueous, plus potassium hydroxide, which is also aqueous, which is going to react to form potassium bromide, which is aqueous, and water, right? And water is going to be a liquid. So we're always looking for that thing that has a different state. In our last example with the silver sulfide, it had a different state. Here we have aqueous, aqueous, aqueous in a liquid, so that's what we're going to look for as well. Then we're going to break down everything into their individual ions. So I'm going to take my red again, and we're going to make an ionic equation. This one's a little bit simpler to do because everything is just a one-to-one pair. So we are going to have from our HBr, that is going to break up into H plus ions and Br minus ions. So it's going to be H plus Br minus plus potassium plus, so K plus OH minus. And those are going to react to form potassium plus Br minus plus H2O. Right? We leave the H2O together because it is in a different state. All right? Just like we did in the last example, we are going to write our net ionic equation by canceling our spectators. So when I look at this reaction, my H plus, well, that was added to our H2O, so I'm going to leave that one there. Our Br minus, all right, I have a Br minus over here, so I can cancel those out. My K plus, well, I also have a K plus here, so they haven't been changed, so I can cancel that out. And my OH, well, it's in my H2O as well. So now I just know that H plus OH minus is going to equal H2O. This is going to be aqueous, this is going to be aqueous, and this is going to be liquid. Right? And this is actually the general reaction for any acid and base reacting whatsoever. Right? So in any acid, right, it is going to donate and any base typically forms OH minus. So any acid and any base reacting with each other are always going to produce H2O. So that's great. There's our net ionic equation. So we've looked at two specific ways that we can create net ionic equations. So what I want you to do now is take a good 15 or 20 minutes in order to work through these 10 questions on page 410 of your textbook. Right? They're all going to be quite similar to the examples we've worked through today. You can work together in groups, and if you need to, feel free to go back and pause as you go through the video to see exactly how I was able to solve these questions. And if you have any questions, shoot me an email, and I will try and answer as much as I can while I'm gone. Thanks, and have a good day.